Let's talk about the cosine of x expansion. And I want to make sure that we go back here because I forgot to add this nth term, this general term here does need to go in our infinite series. So when we talk about the expansion, we do need to include that. So we'll say the negative 1 to the n power, and then we had x to the 2n plus 1 because all of our powers were odd. And then the 2n plus 1 factorial was on the bottom. So that is our general term for a sine of x expansion or a sine of x series. So cosine is going to be similar to sine of x. You're going to see a lot of the relationship there. There's going to be a correlation. If we start with cosine of x, the derivative of cosine is negative sine. And then the derivative of negative sine is negative cosine, just using my trig circle of happiness here. Then derivative of negative cosine is sine. And then we're back. So by the time we get to that fourth derivative, the derivative of sine is cosine, and then our pattern is just going to repeat. Remember, this is a Maclaurin series, so we're dealing with the center being at x equals 0. So cosine of 0 is 1. All of the sine of zeros are going to give me 0. So that one's going to be 0, this one's going to be negative 1, that one's going to be 0, and then my pattern is going to start to repeat. So let's go ahead and tack on that Taylor polynomial piece, right? That x and x to the 0 and x squared over 2 factorial. So remember, technically there's an x to the 0 over 0 factorial here, just don't need it. There's an x to the 1 over 1 factorial, but that reduces to just x. And then we have to start with our x squared over 2 factorial and our x cubed over 3 factorial and our x to the 4th over 4 factorial. So for cosine, all of the odd pieces reduce. So similar to with sine, you're going to have terms reduce because of the 0, but for this, the odd powers cancel, and even alternates signs. So again, I'm going to build the first few here. So my first term would just be 1, and then I would have minus x squared over 2 factorial, and then I would have plus x to the 4th over 4 factorial, and then the pattern would continue, minus x to the 6th over 6 factorial, etc. So the question is, what is that general term? So remember, this is not 1, and this is not 2, and this is not 3 when it comes to the n, because these got reduced out. So really, this is n equals 1. Oh, excuse me, n equals 0. Then this is n equals 1. Then this is n equals 2. And this is n equals 3. So the question is, what is the relationship between 3 and 6 and 2 and 4 and 1 and 2? That's kind of what we're looking for. Now, I am alternating signs. So we're looking at a situation where you're going to have a negative 1. So negative 1 raised to the nth power. Then you're going to have x to the what? Well, if I just multiply this by 2, that's going to get me there. So it's going to be x to the 2n all over, and then the same factorial, 2n factorial. So that's going to be your general term. Let's write that. You want to be careful to make sure, because we start with a positive, when we raise this to the 0 power, anything raised to the 0 power is 1. So that confirms that I'm starting with a positive 1 here and not a negative. If you had created something where this started at 1, this would be very different. So starting at n equals 0 definitely matters. So I've got negative 1 to the n times x to the n, 2n over 2n factorial. So there's your general term. So let's double check and make sure that my interval of convergence is negative infinity to infinity, and it should be, but I'm gonna skip that first immediate step with the ratio test where you have a sub n plus 1 over a sub n. So I'm gonna go ahead and write that as just one fraction instead of a complex fraction. So remember, if I plug in an n plus 1 here, that would distribute. So we would end up with 2n plus 2. So you got to be careful with that. You've got 2n plus 2 here. And then you're going to have 2n factorial. And then on the bottom, you're going to have x to the 2n And then this is going to be 2n plus 2 factorial. These pieces reduce to an x squared, similar to what happened with sine. I'm going to go ahead and factor that out. And you're going to have the limit as n approaches infinity. And remember, dealing with factorials, we just end up subtracting 1. So you're left with 1 over 2n plus 2, and then 2n plus 1. Everything else would reduce. I realize that's really small. But 2n plus 1 and 2n plus 2. Which again, oh, I didn't want to write the limit there. That limit is 0. So when you multiply x squared by 0, you get 0, which is always less than 1. Right? So this is a situation where the interval is going to be from negative infinity to infinity, which we expected, but we did want to confirm it using the ratio test. I'm sorry you couldn't see that. It got a little messy there. So again, same thing happened up here. So the same thing happened up here with sine, and we confirmed that our interval of convergence is everywhere. It's all real numbers. So cosine of x is going to be equal to this infinite series for all x's. There's some other expansions down here that are good to recognize. Really, the only one that I would expect you to see often is probably the ln of x piece. But these other ones are good for you to see and just be able to reference. But none of these will you have to memorize. But you do need to know cosine of x, sine of x, and then the e to the x. That e to the x expansion you're going to see quite a bit. So those three are really important that you not only recognize them, but that you memorize them so that you can use them.